Yeah, okay. Welcome to the first LOPSTR talk, the short presentation. It will be on certified proof checkers for neural network verification. And the presentation will be given by Remi. Thank you very much.
Thank you. Hi, everyone. So, as the chair just introduced, my name is Remi, and I will present our ongoing work on implementing a formally verified proof checker for neural network verification with the Imandra theorem prover. And this is a joint work with Omri Isac, who was supposed to come here but unfortunately could not join us today, along with Passmore, Kathrin, Komandantskaya, and Katz. And for disclosure, Passmore is the co-founder and co-CEO of Imandra, and Imandra funds my research as well. So first, let's start with asking ourselves, why do we need to verify neural networks, and why do we need proof checkers for neural network verification? So as you may well know, deep neural networks, or DNNs, have accomplished groundbreaking results in many safety-critical fields, like autonomous vehicles, autonomous aircraft, medical imaging, but their decision process is opaque to humans, and they are known to be sensitive to input perturbation. So small changes in an input of a neural network can cause large variation in the output of the network. So in order to mitigate this vulnerability, the verification community has been developing analysis tools for deep neural networks called verifiers. But these verifiers themselves are complex pieces of software with a lot of optimization in order to scale to the huge size of neural networks. And so they are also susceptible to having bugs in them. And in particular, Gia and Renard have shown that even a neural network that has been certified by a verifier can have an unsafe behavior because of the use of floating point arithmetic, and so it introduces numerical instability. To check the DNN verifier's result, some of them have implemented a proof production. So implementing a proof is a technique that's been widely used in SMT solvers, and it allows an external tool, the checker, to check the proof externally, and so to add trust to the verifier's result. But then we can ask ourselves, how do we trust this checker? It's itself a piece of software susceptible to bugs. It contains optimization because the size of proof can also be large. But this kind of reasoning opens the way to infinite regression. And in order to cut this short, the answer is to implement a trusted checker, so using a programming language that enables the use of formal methods to formally prove the correctness of the proof checker. And this is exactly our aim with this work. So we implement a novel proof checker for DNN verification, which improves on the existing implementations by offering numerical stability and formal verifiability of the proof checker's correctness. We have also specified the checker's correctness properties, and we've started to verify the checker's compliance with this specification. And in order to implement this verified proof checker, we used, as I mentioned, the Imandra theorem prover. So the goal is to find a trade-off between scalability and trust and verifiability. And Imandra offered, for this use case, a good balance between the two. So its logic is based on a pure higher-order subset of OCaml. So it gives us a higher-order programming language, but also offers the ability to formally reason about the OCaml code or the Imandra code with proof by induction and numerous proof automation techniques. And in the end, we also have the ability to extract the verified code to native OCaml, so to benefit from the native OCaml compiler. So this is good for the scalability. But before I go more in detail in the details of the proof checker, I will talk about DNN verification and what type of proofs are being produced. So to give a brief overview of neural networks, they can be represented as computational graphs, where the input of each node is computed by computing the weighted sum of its parents, and then we apply nonlinear activation function. Here we will focus exclusively on neural networks with the ReLU activation function that's defined here, because it has good performance and it has the benefit of being piecewise linear. So it's easy to reason about. And in a second, we'll see that we had a refinement to this representation. We split the nodes with a ReLU activation function into two sort of subnodes. One is just the result of the... can I point? Sorry. Yeah, one is the result of the weighted sum of the parent nodes, and then the second one is just the result of applying ReLU to this B3 node here. So DNN, the problem of DNN verification is the aim is to decide, given a trained DNN n and a property p over the input and the output domain of the network, whether there exists an input x such that p holds. P is typically undesired property, so if we find a satisfying assignment x, this x is considered as a counterexample and the network is considered as unsafe. And as I mentioned, we consider DNN with piecewise linear activation function, and this allows us to formulate our verification query as an ensemble of linear and piecewise linear constraints. So here we have a representation of verification constraints. We have a neural network a property, a safety property. So the network is encoded in linear constraints with bounds for all the variables. And then the ReLU activation functions are encoded as piecewise linear constraints. And so very broadly, the algorithm uses linear programming to try to solve the linear constraints. And if it cannot find a conclusive result, it will split the piecewise linear constraints and create subqueries with the added information from the piecewise linear constraints. And so this creates a tree search, a tree structure for the search of the algorithm. So the result in each leaf of the tree is determined by the LP solver. Now onto the proof production. So we rely on previous works by Omri, Isac, and colleagues, and they use the Farkas lemma to produce proofs for an LP solver based on the simplex algorithm for DNN verification. So the linear constraints that I showed earlier are normalized and encoded in a matrix called the tableau. And we try to find an assignment for the variable vector x bounded by the bound vectors L and U such that it satisfies the constraints encoded in the tableau. And in particular, they show, sorry, I can see that it's not very readable, but in particular, they show that if the problem is unsatisfiable, there exists a vector of coefficient, a column vector W, such that for all variable vector x with bound NLU, the linear combination of the tableau rows with the coefficients in W is bounded by a strictly positive upper bound. So the result is strictly of the linear combination scalar x is strictly negative. And so thus, W is a proof of the constraints system unsatisfiability. And moreover, this vector can be constructed during the execution of the simplex algorithm. And what the existence of this Farkas lemma allows us to do is that we can check the result of the simplex algorithm in linear time. Instead of having to rerun through all the steps of the iterations of the simplex algorithm, we can multiply or compute the linear combination of the tableau rows, check if its upper bound is negative, and we know if the result is valid in linear time. So the proof certificate matches this tree structure from the initial query. It contains all the information of the initial query, the tableau, the upper bounds, the lower bounds, and then the proof tree matches this search tree with each embranchment corresponding to a split over piecewise linear constraints. In the nodes, there are information that I won't go into details in now, but that refer to the dynamic bound tightenings. And so in the leaves, the vectors from the Farkas lemma that I just introduced are stored and allow us to check the proof. And so the proof checking algorithm consists in traversing the tree and checking in the non-leaf nodes if the split are correct. And again, I'm not getting into too much detail here, but checking that the bound tightening lemmas are correct. And more importantly, in the leaves, we check the contradiction vector, we compute the linear combination of the tableau rows and check that its upper bound is indeed negative. And if all the leaves, if the proof checker checks that the Farkas lemma are correct in all the leaves, then it means that the proof is correct. This is for the case where the problem is not satisfiable. Of course, if the problem is satisfiable, then the simplex algorithm just gives us a satisfying assignment, and it's straightforward to check if it's valid or not. So now we can arrive at the implementation in Imandra of this proof checker. So here we can see what Imandra code looks like. So we can see that it's a valid OCaml syntax, as it's just a subset of OCaml. And so what we did was adapt the existing proof checker implemented in C++ into the Imandra's functional programming language. And this in particular shows the definition of the class for the C++ implementation and the type for the Imandra implementation of each proof tree in the proof certificate. And one thing that we can already see here is that in the Imandra implementation, the structural correctness of the proof tree is guaranteed at type level, so we don't have to have a valid function that checks if the structure is valid or if the proof tree has all the necessary information. As I mentioned earlier as well, Imandra supports arbitrary precision real arithmetic, which allows us to avoid the numerical stability problem. It does so by using a native OCaml library, which itself is an interface for the GMP library. And so this part, the GMP library, is not itself formally verified, but it's well tested and standard enough that we're happy with having that as part of the trusted code base. I'll go quickly over these, but basically the fact of having a high-level language, basically OCaml with theory for reasoning about standard data structures like lists and maps, allowed us to experiment with different data structures. So the standard inductive definition of lists in OCaml, but which was better for the verification that I'll mention in a moment, and then an implementation of sparse lists that are implemented as binary trees. Again, going quickly over this, but we also it also allowed us to experiment with different verification mode, which allows us to balance between scalability and trust. And in the end, we evaluated our implementation on a number of examples from the ACAS-XU neural network verification benchmark. So proofs generated by the Marabou proof checker on examples from the benchmark. And from what we saw is that so we compared with the existing C++ implementation of the proof checker, and from what we saw is that our best comparable version of the proof checker is less performant than the C++ implementation, but that was expected because it wasn't as optimized as the C++ implementation. But it was a linear overhead, so that was quite satisfying. And we can also see that there are definitely optimizations to be made because, for instance, the sparse vector implementation is faster for a mode and slower for the other mode of verification. So we know we have avenues of amelioration. Now I will present the correctness specification and how we verified the first part of this correctness specification. So to go back to this definition that I gave earlier, so what we want to prove is the second part, the unset case of this theorem, is that in our implementation, if the linear combination of the tableau rows has a strictly negative upper bound, then the constraints are indeed unsatisfiable. And to do that, we started with using the same representations of the tableau as a matrix as earlier, but it turned out that it was easier to redefine slightly the problem, and so switch from a matrix-based representation to linear polynomials. So we give definitions for the linear combination and positive linear combinations of polynomials. And now we consider a system S with normalized equalities P1 to Pm and inequalities with polynomials Q1 to Qn. And what we want to prove now is that if there exists a linear combination I of the polynomials Py to Pm and a positive linear combination C of the polynomials Q1 to Qn, such that I plus C is a strictly negative constant, then S is unsatisfiable. And the proof of this goes as follows. So retaining the same notation as before, if we have the linear combination and the positive linear combination of the equality and inequality polynomials I and C, such that I plus C is strictly negative, then the polynomial function I plus C, or the evaluation of I plus C, is strictly negative. And on the other hand, the propositions in S imply that I of x is equal to 0, because I is defined as the linear combination of P1 to N and P1 to M are all equal to 0, and similarly, C of x is greater or equal to 0. We then have that I plus C of x is greater or equal, or is positive, so this leads to a contradiction, and so this is a proof that S is unsatisfiable in this case. To prove this, we define the theorem we want to prove in Imandra. So the arguments to the Imandra function are implicitly universally quantified. We have S the system, X the variable vector, C is the vector of all the coefficients for for computing I and C. Well-formed is just, so we have a Boolean valued function with an implication. So in the preconditions, well-formed means that the dimensions of all the structures are coherent, so that Imandra doesn't consider empty lists or whatnot. And check certificate computes that the linear combination I plus C is strictly negative. And eval system, it just checks that the variable vector x satisfies the propositions in S. So to prove this theorem quickly, first we prove the first part of the theorem. So if I plus C equals 0, then the evaluation is strictly negative. Here we can see the annotations, the guides that we give to Imandra to prove this. So there are other lemmas that were defined outside of the functions, but they're automatically called and applied by Imandra. So this is all we need to give to prove this lemma. Then we prove the second part of the lemma, and finally we use again this annotation applied to use the two previously defined lemmas to prove the main theorem. And so in total, the proof for the correctness has 15 lemmas and 233 lines of code, which we thought was pretty succinct and elegant. And to conclude very briefly, so we proposed the new implementation of the proof checker for DNN verification. Our implementation offers better numerical stability, greater verifiability. We started to specify the correctness property and to verify it. Now there are other parts of the proof checker that we still need to verify, in particular the dynamic bound tightening lemmas that I mentioned briefly, and so this is ongoing work. And in future work, we also aim to optimize the performance and integrate the verification of the neural network with the verification of a larger system that contains machine learning-enabled components using this proof-checking facility. So that's me. Thanks for your attention. I'll be happy to take any questions.
Questions or comments?
Hi, Thomas Jensen. Farkas lemma has been used to also to certify program analysis, like to produce certificates for polyhedral analysis in the past. So in my group, we use this to do to build a proof carrying code framework where you use Farkas lemmas and the witnesses that you get there to certify this. This was built in COG. Did you consider using that instead of starting all over?
I actually, I didn't find, I looked for implementation of the proofs of Farkas lemma in different theorem provers, and I found the Isabelle Hall one, but not the Koch one, so I'd be interested if you could share it with us.
Yeah, it's online. There's one in Rennes, and I think the David Monio's group in Grenoble also built one. So.
All right, and we considered using Koch, but first, I'm not a specialist in Koch, and I have little experience in it. But from what I saw, the advantage in using Imandra is that we had expertise in programming in OCaml, and so we could directly leverage that to implement the algorithm and verify it in the same environment, if that makes sense.
So it would be interesting to hear the comparison of the two approaches.
Yeah, that would be very interesting. Thanks for the suggestion.
Thank you.
Other questions?
Okay. So it's a minor technical question that in the eval system, when you were evaluating this set of constraints, did you define your own evaluation, or did you use the native data structure of the theorem prover that you are considering?
No, so we implemented our evaluation function, and one thing that I did not mention is that the evaluation also checks that the coefficients for the more in the check certificate function, we also check that the coefficients for the inequality polynomials are positive. So we all define it's all defined.
Correct. But my question is more about like eval system SX. Is that something that you you defined what it means to evaluate it, or did you use do you convert it to native data structure of the theorem prover that you're using?
So. Right, I see what you mean. So in fact, we're using mostly native data structures. So for instance, here the system is just type alias for a list of a native list of expressions.
Okay.
And so we use native data types.
More questions? Yeah, then maybe I have a question. Looking at this slide with the 15 lemmas and 233 lines of code. Okay.
Oh. This is working.
Would you have an intuition? You show it's 15 lemmas, 233 lines of code. Why it is so elegant? To what it can be attributed?
Good question. I think that since Imandra already has a lot of lemmas for operations on lists and real arithmetic, we didn't have to redefine any. And since we're using the native list data type, we didn't have to redefine any of the properties for that. For instance, I know that a lot of lemmas for the length of the list are reused So I think this is taking advantage of a lot of Imandra's proof automation. Also, one thing I noticed with using greater automation with Imandra is that we arrive at very short proofs, but compared to the small experience I have in Coq, it's sometimes harder to figure out which lemma is missing to advance the proof. But once you figure it out and you know where Imandra is trying to advance the proof automatically, and you know which element is missing, then it can be quite elegant.
Yeah, thank you. Other questions, comments? Yeah.
Thanks for the talk. So you have a proof of Farkas lemma, but do you relate it with a proof about something in the DNN?
That's a very good question. So what we relate it with the proof checking algorithm that checks the proof in the DNN. So the check certificate function that it's the main function that we verify here, for which we verify the correctness, and this is the one that's used in the main proof checking algorithm that's defined. And so this proof checking algorithm it verifies that the property over the DNN holds via basically in the system, the polynomials for the linear constraints encode the DNN, if that makes sense.
Other comments or questions to our speaker? Yeah. If not, then let's thank our speaker for an introduction. Thank you very much.